Hey everyone, welcome back to CodeAccessHub. So, we're diving right back into our 30-part series on the most fundamental papers in AI, all picked by Ilya Sutskever himself. We're on part 3, and this one's a really cool one. We're going to tackle a super elegant idea that connects two things you probably wouldn't think go together: finding patterns in data and, believe it or not, compressing that data into the smallest possible file. It's an idea that, honestly, changes how you think about learning itself. So let's get into it.
All right, so the paper we're digging into is called A Tutorial Introduction to the Minimum Description Length Principle. And look, don't let that word tutorial throw you off. This thing gets right to the core of a massive question in all of AI and statistics, which is, when you've got a mountain of data, how in the world do you find the real signal, the actual pattern hiding in there? And the answer, as we're about to see, has everything to do with compression.
Okay, so here's the game plan for this explainer. First, we're going to talk about a classic headache, overfitting, that really sets the stage for everything that follows. Then, we'll get to that big aha moment of MDL, this link between learning and compression. From there, we'll look at how the idea grew up, from a kind of simple concept to a much more refined, powerful tool. We'll even put it head-to-head with the famous Bayesian approach. And then, we'll bring it all home. So anyone who has ever worked in machine learning knows this problem inside and out. It's something you deal with every single day. You get a set of data, right? And your job is to build a model that explains it. But here's the trap. It is so easy to build a model that's way too simple and just misses the point entirely. Or you can go the other way and build something so ridiculously complex that it's just memorizing the noise. The real trick, the whole game, is finding that perfect, just right model in the middle. And this picture, it just nails the dilemma perfectly. On the left, that's underfitting. You can see we've tried to explain this obviously curved data with a simple straight line. Yeah, it's simple, but it's just wrong. It's completely missing the real pattern. Now look at the right. This is the opposite problem, overfitting. That crazy squiggly line, it hits every single data point perfectly. But can you see what's really going on? It hasn't learned the pattern at all. It's just memorized the random wiggles, the noise. This model would be completely useless if you tried to predict any new data points. Absolutely useless. So that brings us to the big question, right? How do we actually find that perfect balance between being too simple and too complex? This is really just a new school take on a really old idea, Occam's razor. The simplest explanation is probably the best one. But what does simple even mean mathematically? How do you turn that philosophical idea into a formula you can actually use? And that is where the minimum description length principle, or MDL, makes its grand entrance. And it's just a total reframing of the entire problem. It basically says, hey, what if the goal of learning, of finding patterns, is actually the exact same thing as another goal, beta compression? This quote right here, it flips the whole idea of learning upside down. Just think about it for a second. If you have a totally random string of coin flips, heads, tails, heads, heads, tails, you can't really compress it. Why? Because there's no pattern to learn. But what if you have a string of 1,000 A's all in a row? Well, you can compress that down to a super simple description, 1,000 A's. That very act of finding the short description, the compression, that's the learning. And here it is, the principle laid out formally. The best model isn't just the one that describes the data with the fewest bits. No, it's the one that makes a two-part description as short as possible. Part 1 is the length of the description of the model itself. Think of this as the complexity tax. A really complicated polynomial costs a lot of bits to write down. Part 2 is the length of the description of the data using that model. This is the accuracy part. If your model is good, the data becomes predictable, and that makes it really easy to describe. The goal is to make the total package, the whole shebang, as small as you can. Okay, so how do we actually use this? Well, the perfect ultimate version of this idea is something called Ideal MDL. It's based on a mind-bending concept called Kolmogorov complexity, which is basically the absolute shortest computer program you could ever write to generate your data. It's the perfect measure of complexity. The only tiny problem? It's literally uncomputable. You can't actually find it for anything non-trivial. So what do? The entire history of MDL has been this quest to create practical versions that get as close as possible to this ideal. And that journey starts with a simple, intuitive version, often called Crude MDL, and then we'll see how it got sharpened into something way more powerful. So this crude two-part code is our first real practical attempt, and it's exactly what we just defined. It's a brilliant way to choose between models. Step 1, you pay a cost, L of H, just to send the model's blueprint. A simple line is cheap, a super complex polynomial, that's expensive. Step 2, You use that model to encode the actual data. Now, the better your model captures the data's real pattern, the shorter that description, L of D given H, is going to be. And this is the magic of MDL. It automatically finds the sweet spot. You can't just cheat by picking a ridiculously complex model to make the data description tiny, because the cost of describing the model itself, L of H, would just go through the roof. It's a built-in trade-off. But, that crude approach had one little issue. The cost of the model, that L of H, could be a bit subjective. It depends on how you decide to write it down. So refined MDL came along to make things much more objective. Instead of that two-part code, it uses this really clever single universal code. And get this, the complexity penalty is no longer about how long it takes to write down the model. Instead, it's about the model's flexibility. Think of it like this. A really powerful model family, like those high-degree polynomials, is so flexible it can fit almost anything, even pure random noise. Refined MDL calculates a penalty based on that raw power, how much random data a model class could have fit. This is what's called normalized maximum likelihood, and it totally removes that subjective part, making the whole process way more rigorous. Okay, so if you've spent any time in machine learning or stats, your spidey senses might be tingling right now. This whole thing might sound a little bit like another major framework you've heard of, Bayesian Inference. And you'd be right. They both try to solve the same problem, balancing complexity and fit, but, and this is key, they come at it from completely different philosophical angles. All right, let's just lay it out side by side. The guiding principle of MDL is data compression. It's Occam's razor in a formula. The guiding principle of Bayesian inference is updating your beliefs using Bayes' rule. MDL asks, what's the shortest possible description of this data? Bayesians ask, what's the probability of my hypothesis now that I've seen the data? And here's the biggest difference. Bayesian methods require a prior. That's a belief you have to state before you even see the data, and that can be subjective. MDL, on the other hand, really tries to avoid that. It doesn't ask what you believe, it just asks for the shortest code. That focus on an objective description length is what really makes it unique. And this really brings us to the core takeaway of this whole thing. The true power, the beauty of the minimum description length principle, is that it gives us a rock-solid mathematical foundation for Occam's razor. It's not just some nice philosophical guideline anymore. That penalty for complexity, whether it's the L of H term or that fancier flexibility cost in refined MDL, it's not some random number you just pull out of thin air. It falls directly out of the cold, hard math of information theory and coding. By just trying to find the shortest possible explanation, you are automatically forced to find that perfect balance, and you avoid overfitting in a really principled and beautiful way. Getting your head around these deep, powerful ideas like MDL is exactly what this series is for, breaking down the papers that really built the foundations of modern AI. And trust me, this is just one of the huge ideas we're going to be covering. So if you like this breakdown and you want to catch the other 29 explainers on Ilya Sutskever's must-read list, please make sure you're subscribed to the CodeAccessHub YouTube channel. We're going through all the papers that built the world of modern AI, one deep dive at a time. So I'm going to leave you with one last thing to think about. The MDL principle kind of suggests that finding a fundamental law of nature, discovering something like E equals mc squared, is really just the same as finding a ridiculously shorter way to describe all of our physical observations. So if the best scientific theory is just the best data compression algorithm, what does that imply about the very nature of science itself? What are we even doing when we discover a truth? Something to chew on. Thanks for watching.